Okay, so let's talk about describing and analyzing data, looking at section 8.3. So the first thing to talk about is measures of central tendency, or measures of center. So that's just a fancy way of describing mean, median, and mode. And remember that mean means average. So if you've got a bunch of numbers in your data set, and you want to know kind of what is the center of the data set, or what value is most representative of this data set, we have three different ways to calculate that. The first is the mean. Well, they don't come in any particular order, but in the order that we're going to talk about them. The first one is the mean, and you'll see in the text on page 403, there's a fancy definition for mean with this Greek letter mu being the population mean. But if you look at the mathematical description there, it's a fraction with the numerator just being the sum of all the data points in the set. So these little subscripts just keeping track of how many there are, and I'll say there's n number of elements, and then how do you get an average? You add up all the numbers, and then you divide by however many there are. So where n here would be the entire size of the population. And then we have the sample mean, which is denoted by x bar, so x with a bar above it, x bar. This is the sample mean, so the mean for some, or the average of some subset of the population, but it's the same formula. It's going to be however many things you're summing up. I won't use the same n, capital N, because this is supposed to be a subset, but the formula is the same. If you've got some sample and you want to find the average of it, just add up all the numbers and then divide by the number of elements in that sample. So these both may look weird, but they're just averages. That's all they are. All right, the median. So what I'm going to do for all three of these is describe them, and then I'm going to run one example to show you how these all go, because you're probably familiar with these measures of center already. All right, so the median now. The median is going to be the literal center of the data set. So the median is the median of a data set. So when I say center, I mean like numerically, the numerical center. In other words, the data set has to be in order. So we can say the median of a data set is the central value for an ordered set. So if your set is not ordered, you've got to write it in order to then find the median. If there are two, so what if you've got like 8 elements in your set and you count in, so then you're counting in towards the center, but there are 2 numbers in the middle? You just take their average. If there are 2 numbers in the center, take their average. Okay. Then we've got the mode. And the mode is just the value that appears the most. Is the value that appears the most. We can have different types of modes. First of all, a set doesn't have to have a mode. If everything appears the same number of times, like if our number set is 1, 2, 3, 4, 5, 6, then there is no mode because nothing appeared the most. But what if our number set was 1, 1, 2, 2, 3, 4, 5, 6? Then that would be called bimodal because it would have 2 modes. It would share a mode between the 2 values that were repeated the most. And if it's got more than 2 modes, it's called multimodal. So mode, you can have a lot of different things going on. You can have a single mode, which is like the most normal example. You can have no mode at all. or you can have multiple modes. And if there's two, we call it a bimodal. And if there's more than two, we call it multimodal. Alright, let's run an example. So this example is not from the text. I'm just going to make up an example where we find all of these numbers, and I'll make it an interesting example, meaning we'll do one where we have to do this business about finding the average of the two central numbers to find the median, and I'll also make it multimodal, so you see what that means. So let's, can we just call this, we'll just call it example 1, but not example 1 from the text. Okay, let's say, alright, so let's say this is our data set. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 numbers. We have 14 numbers. Now, in this problem, I'm going to ask for the mean, median, and mode. It's not really important in this context that I tell you whether it's a population or a sample. Later, we're going to talk about measures of dispersion, and we're going to talk about standard deviations. And if I ask for that, then I do have to tell you whether this is a population or a sample. But for the purposes of finding mean, median, and mode, it doesn't matter. It doesn't matter, because median and mode are the same no matter what. And mean, remember, population mean and sample mean, it's the same thing, just using a different little letter to denote them. And I'm not even going to use one of those letters here, because I'm just going to keep it generic and just say mean is equal to, and I know I counted up 14 numbers, so that's going to be what I divide by. And I'm going to take the sum of all of these. I'm going to take the sum of all of these. So I'm going to have 16 plus 13 plus 14, 13, 13, 2, 17, 20, 17, 17, 20, 15, 15. Ooh, barely fit. Okay, good. Let me count these up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, good. And now I'll just calculate this in my calculator. In fact, your calculator may have a button on it if you've got a scientific calculator for calculating averages automatically. And there is a part in our textbook that tells you how to calculate these things quickly. Example 7 will tell you how to do it quickly. Actually, it tells you how to find the standard deviation. Anyways, so let's see. Okay, I'm going to make a note up here. We'll round to the nearest 10th place. So my mean is, oh, where'd it go? There it is. 15.1 is what I'm getting for my mean. So that's the average. That's the average. So I just want to talk about this a little bit before we go into median and mode. 15 may seem a little low because there are 3 17s and 3 20s, right, and a 16. Those are all higher, a lot higher than 15 when you compare them to 13 and 14 and 15, right? But it's this 2 that's kind of messing things up a little bit. This 2 in this case would be called an outlier. So we can make a note here. The 2 is an outlier because it's acting differently. Our data is pretty much grouped around like 17, 16, somewhere around there. It's definitely between 13 and 20, right? The 2 is an outlier because it's much lower compared to the other values. Okay. So depending on what you're trying to do with your data, you may want to discount that 2. It just depends. All right. So the median now. So for median, I'm not going to put equals. I'm going to put a colon because we're going to need to do some work first. And it's not really an equation like mean is. We're going to have to put this in order numerically. So I'll start here and say the 2 is definitely first. The next highest value are these 13s, and I've already noted there are 3 of them. And then of course the 14 is next, and there's just one of those. Right? Yes. And then there are 2 15s and a single 16. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. That's right, there should be 6 more because I've got 8 listed here, and there are 6 more because there are 3 17s and 3 20s. So we do write all of them, even if they're repeated, we write all of the values. Now to find the median, I just count in until I find that central value. So the easiest way is literally write it down and just start crossing off. Even if they write them in order for you on an exam, still write it down on the paper in front of you. Alright, so here we run into the issue where we have 2 central values when we're trying to find our median. So our median then will be the average of these 2, which means the number that's in between these 2, which of course will be 15.5. Just 31 divided by 2, right? So our median for this set is 15.5. There we go. Now I can say equals. Now note for both of these, median and median and mean, neither one of these numbers are actually in the data set. Like 15.5 is not actually in the data set, and 15.1 is not actually in the data set. That's what it is. That's how it's going to be in general. Now, a lot of times your median will be in the center. If you've got an odd number of values and you're counting in and you end up with a single central value, then your median will literally come straight from the data set. But in this case, so in general, it's not true, because if you have an even number of data points, then your median is going to be some average of those 2 that'll probably not be in the data set. And your mean is almost never in the data set, just because of the nature of how you find mean. Oftentimes it is a decimal number. Now mode, on the other hand, will always be in your data set. So let's find the mode. Now once you've found median, the mode should be really easy to note, because you've already got all the numbers like listed, and we notice that there are 3 13s, so we're looking at 13. There are 3 17s, and there are 3 20s. Those are all the modes because they all appear 3 times. If I had drawn one more 20, so there were 4 20s, then the mode would just be 20, because the mode is whatever appears the most. But since it's the most is 3 in this case, these numbers appearing 3 times, then it's shared between these 3 different values. So this set would be called multimodal. These are the answers to 2 different questions. The specific question, what is the mode, you would say 13, 17, and 20. And then if someone said, what kind of mode is it, or what kind of mode does this set have, or how would you characterize this set by its mode, you would say it's multimodal. And like I said, these numbers will actually come from the data set. Your mode will actually be in your data set. There's no weirdness. Well, unless there's no mode, right? If all of these had only appeared once, or if they all appeared 3 times or something like that, then there would be no mode. Okay, let's talk about measures of dispersion. These were measures of center, finding the center of a data set. Now let's talk about measures of dispersion. Dispersion just kind of meaning how things are being dispersed, how they are spread out. The first simplest one is called the range. You probably all remember this. The range is the difference in the largest and smallest values. So from our example a second ago, our range would have been 20 minus 2, because remember, difference means to subtract. So our range for that set would have been 18, which is a pretty big range for considering how these numbers, the size of all these numbers. So an outlier is really going to mess up your range. If that 2 wasn't there, our range would only be, 7? 20 minus 13, right? If that 2 wasn't a part of the set. So outliers like this 2 are really going to give you a large range. The other measure of dispersion that we really want to spend some time talking about is standard deviation. Standard deviation. If I could remember how to spell. Okay. So standard deviation tells us kind of how spread out a data set is. It has a crazy formula for it, but it's not as bad as it looks. And it does have 2 different formulas, one for population and one for sample, but they're really very similar. There's only one little difference. So the standard deviation for a population is going to be, we're going to talk about what it actually is for a data set, but first I just want to get this formula out of the way and talk about what these symbols mean. First of all, we all know that's square root. And then inside we have this capital Greek letter, sigma, meaning sum, and then we have x sub I, so that's going to be some data point like x1, x2, x3, etc., minus that population mean squared, all over n, which was the size of the population. You'll see the standard deviation for a sample super similar. It's going to be S instead of, oh, I didn't even say, that's that Greek letter is it's a sigma, lowercase sigma, and that's an uppercase sigma. It's like S, Greek S for standard deviation, and this Greek capital S stands for sum, like addition. It's just a shorthand way of writing like a giant addition problem. So in here we have the sum of the xi's minus, of course, the sample mean instead of the population mean, and then instead of divided by the entire sample size, which would be lowercase n, we divide by n minus 1. Okay. Okay, so all these letters meaning the exact same thing they did in mean. So you can see standard deviation is going to be a long calculation, and that's why your calculator is going to have an automatic way to do it for you. So let me actually say a little bit about what standard deviation really is. So like, the easiest way to talk about it is to draw a picture. If I had some data set all laid out here on a number line, and I just kind of measured my data with a curve here, so a bell-shaped curve, a distribution is what we would call this, and my mean, let's say my mean is right there in the center because that's where the mean would be. If all of these are different data points and I've constructed a distribution out of them, so I'm seeing this like clumping around the mean, so like for example with the numbers I wrote earlier, the 2 would be all the way down here as an outlier, and right around here would be 15.1 in fact, and then the 20s might be over here and the 13s would be here. Anyway, so standard deviation, assuming that we're dealing with a population, would, well actually no, in either case, but I'll use the population symbol, this little sigma for this example, is just going to tell us kind of how far away from the mean we are. So this point here would be the mean, the average, plus a single standard deviation. And this here would be the average minus a single standard deviation. So how is this useful, and like still like what does it mean and everything? There's a rule called the empirical rule that says that roughly 70% of your data is always going to fall in this range, we say within 1 standard deviation of the mean. That's what I've drawn here. This is within 1 standard deviation of the mean. So a standard deviation this way, subtracting, and a standard deviation this way, adding. So if you were like taking a test, like the ACT or something like that, and they tell you like where you fall in like percentage-wise, or they might even tell you like what the average score is, and then what the standard deviation is, then you can know based off of the average score and the standard deviation whether you fall in 1 standard deviation or not. So if you fall within 1 standard deviation in either direction, that means you're pretty much like around average. If you fall outside of one of those, that means you're very far from average in one direction or the other. And in fact, the empirical rule says that 70%, it's actually 68% of the data should be within 1 standard deviation. But if we go to 2 standard deviations, so if I subtract another, because standard deviation is just a number, so if I subtract it again, so minus 2, and then add another one, so average plus 2 standard deviations, out here, that from here to here gives me 95% of the data. So nearly all the data is going to fall within 2 standard deviations of the mean. So this is just how we use standard deviation. It's just a really useful tool for talking about how spread out a data set is. Okay. Let's actually do some calculations. I am going to do the calculations by hand. In fact, I'm probably going to do them for our example number set. But you should make sure you know how to do it with your calculator. Example 7 in this section on page 411 shows you how to use it. Shows you how to find standard deviation if you've got one of the 2 calculators, a TI-30 or a TI-83 or 84. It's going to show you. It literally like lists. It literally lists the buttons that you need to press in order to find the standard deviation. I would definitely make sure you know how to do that. And if you don't have one of those calculators, all you're going to do is you're going to go to YouTube, you're going to type in the name of your calculator and then standard deviation, find a good video that shows you how to do it. But I'm going to show you how it goes if you were to do it by hand. So the first thing you need is the mean, right? So let's assume, let me write some stuff down before we get going. Let's assume the data let's assume the data from sample 1, from example 1 is a sample, meaning I will use this formula. Okay, so it's standard deviation is a big square root of the sum of each data point minus the average all over little n minus 1. Alright, so how the heck does this go? Well, first of all, I need the mean, but luckily we've already found that to be 15.1. So that would be your first step, find mean. Find the mean. Oh, squared. Did I put that? It's supposed to be squared. I think I forgot that back here. Whoops. Okay. Alright. So now what we're going to do is we're going to follow our order of operations that tells us to find the sum of the squares of all of these differences. So this part here, the sum of each xi minus the average squared, is going to be, so you'd write your first data point, xi, and just for convenience, I'm going to write them in my numerical order, which I've kind of messed up the list here, but I can still make them out from earlier. So I'm going to move this. I'm going to assume that you already have that written down. So first one would be 2 minus 15.1 squared. Plus, see, this is where the sum is coming in. So I'm taking the sum of all of these. So this is the first one. And then the next one would be 13 minus 15.1 squared. Okay, that's the second one. And I need 14 of these. Remember, there's going to be 14 of these sums because there are 14 elements. So the next one is going to be another 13. Another 13. And at this point, I'm going to pause. Okay, there they are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 14. Now that I've got it all set up, I need to compute all of these. That means finding this difference and then squaring. Find difference, then square. Find difference, square. Find difference, square. And then I will add them all up. So, as you can see, trying to motivate you to go take the time to figure out how to use your calculator, because if you don't know how to use your calculator to do this automatically, you will have to do this by hand, just like I'm doing, and it sucks. There are so many places you can mess up. So I'm going to pause again. Okay, there they are. This is me finding the difference and then squaring all of these numbers. You see, this one is massive compared to the other ones because this is the one that came from 2 minus 15.1. So this one is very far from the mean. So it's going to give me it's going to make my standard deviation go up. All right, now I got to add all these up. Okay, I noticed I actually missed one, so put that back in there. And then I got 269.74, and I'm not rounding yet. I won't round until the very end. And I'll just have to round to whatever I was told to in the problem. Okay, so now what I've got so far is this giant sum. This part, all of this was just this part, which falls right there. Okay, so I'm on the home stretch. I've done the brunt of the work. But I still need to do the division and the square root. So s is equal to the square root of the sum of all the xi's minus the mean squared all over n minus 1. That is still under the radical. So right now I've got square root of 269.74. That's what I got for my sum. And then over n minus 1, so that's 14 minus 1, because there are 14 elements in my sample. Okay, so that's going to be square root of 269.74 over 13. And I need a calculator to do this, so I'll divide first. 269.74 divided by 13 is a crazy number that I'm not going to round. I'll round it so you know what I've got on paper, but in my calculator, I'm going to leave it as it is with all of its digits, and then I'll take its square root. But just for the sake of writing it down so you can, if you're working along, so you see that you've got the same number, it's like 20.74923, etc. So then I would just punch that into the calculator, or rather leave it in the calculator and just smash that square root button. I'm getting 4.56, rounding to the nearest hundredth. Because it was 4.55. Oh, 4.555. So yeah, rounded to the nearest hundredth is 4.56. Okay, that is my standard deviation for this sample. Alright. Okay, so let's talk about what this means. What does this mean, that S is standard deviation is equal to this? This means that roughly 68%, that I'll just say 68% of the set of data if it's a nicely behaved data set, should fall in what range? One standard deviation around the mean, right? What was the mean? It was 15.1. So I'll take 15.1. I'm trying to find the range here where this, and when I say range, I don't mean range in the sense of a highest minus lowest. I'm not talking about that range. I mean like the range of the interval that this data will fall into. So I'll take 15.1 and I'll subtract a single standard deviation, and I'm getting 10.54. And the other value will be 15.1, so that average, plus a standard deviation, 4.56, 19. Okay. It is an interval, so I'll put it in this interval notation. 68% of my set should fall into this range. So what was my set? 16. Okay, so the 13s fall in there. The 2 does not. So if I listed all of them, it was 2, 13. Where is it? There are 3 13s. A single 14, 2 15s, a single 16, and then, whoops, 3 17s. And 3 20s. And what numbers are going to fall in that range? Do I have a pretty color? How about purple? This one, 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 and this one. Okay, so how many is that? That is 10 out of 14. 10 out of 14. 10 out of 14. 10 out of 14 is approximately what percentage? Remember how to do that? Just do 10 divided by 14 multiplied by 100%, and it's roughly like 71%. So we see that our data set does obey this rule. It is nicely behaved enough. We don't have tons of extreme values that are making our data set weird, that it is nice enough that it behaves according to the empirical rule, which is what this rule is called. The rule that tells you how much of your data should fall within a single standard deviation or more than one standard deviation is called the empirical rule. Let's see if it's behaved well enough to have 95% of the data within 2 standard deviations. Let's do that on the back here. So a single standard deviation got us a pretty big range. If we did it again, so if I took that, I gotta see what it was. So 10.54 minus another standard deviation. So this would be the mean 15.1 minus 2 of these would give me 5.98. Oof. 5.98. And the higher value, so 15.1 plus 4.56 plus 4.56 is 24.22. Okay, how much of our data is going to fall into this? Well, everything except for the 2, right? Everything except for the 2, because the only numbers that weren't already in there were these 20s and the 2. We see clearly the 20s are going to fall in, right, obviously. And the 2 is still left out, though, because the 2 is an extreme outlier. And according to the empirical rule, do we have 95% of our data? Well, we have 13 out of 14. What is that as a percentage? 13 out of 14 is roughly 93%. So because of that too, our data is not so nicely behaved that it follows the empirical rule for it's really close though, isn't it? It's really close. And the empirical rule is an approximation. It's an approximation. And it actually goes a little bit further. It says that if you go 3 standard deviations away from the mean, that you would have 99.7% of your data, which for us, this is such a small example, there were only 14 elements. You're not going to, either the 2 will be in there, which would give us 100%, or it won't, which would give us 93% again. Would it be in there? Another standard deviation out? Well, if I took 5.98 5.98 subtracted another standard deviation? Yes, because that would be 1.42. So we would have 100% of our data within three standard deviations. They have a nice little picture of all of this on page 413. Right there. You can't see it that well on camera, but if you look at this page, they have a nice little picture with all the little standard deviations away from the mean written down here. Okay. Okay, so that is it for 8.3. You need to make sure that you know how to find the standard deviation on your calculator. So do some digging on YouTube to figure out how to do these automatically so you don't have to do it by hand. And run the example we did once you think you know how to do it to make sure you get the same standard deviation that I did. And if you cannot find any reliable videos on YouTube, or you did but you're still not sure, you have a slightly different model of calculator or something like that, or if you just have questions about any of this in general, then join our tutoring sessions. Oh wait, we won't have one before the test, so never mind. Send me an email and we will talk about it. And I can get you straightened out with the calculator business for sure. All right.